Hello, in this video we're going to be looking at the pigments involved in photosynthesis. So let's not waste any of your time, let's get right to it. Now, when we're talking about the pigments involved in photosynthesis, one thing we want to mention right at the beginning, is that those pigments are what absorbs the light energy from the sun, and of course the sun sends down this series of waves. Sends it out everywhere, and again, a portion of it lands on Earth. But this idea of the electromagnetic spectrum, hopefully you're familiar with that phrase, but that's the range of wavelengths that stretch out, from the gamma rays to the UV rays to the visible light portion, the part that we can physically see, to the radio waves, the TV waves, microwaves, that kind of stuff. But the idea of these various levels of energy are different. It's essentially the same component, but the wavelengths are different. When I say wavelengths, I'm talking about the differences between two crests. If you're looking at a wave in a line pattern, the distance between those two crests is a wavelength. And so really the only difference between a radio wave and a gamma ray is the fact that the gamma ray wavelength is a lot smaller, and when it's a lot smaller, it's more powerful. You can think about it being punched in the arm. Okay, a radio wave might punch you in the arm once every 3 or 4 minutes. Okay, over time, being punched in the arm can leave a mark eventually. So it's not a great metaphor, because the radio wave will never hurt you or be harmful to you. But a gamma ray would be like being punched in the arm every second. Okay, so it's just a matter of frequency. So it's the same energy, just at a much higher level. That's the idea to think about these energy lights. But these photons, these particles of light that the sun sends out, got these bundles of energy, again, as I mentioned, anywhere from a nice soft gentle radio waves out to the powerful gamma rays. If you want to think about how powerful gamma rays are, I know it's a fictional movie, but the idea of the glove in Infinity War and Endgame, the Marvel movies, that thing had so much, as the Hulk character described it, as just a bundle of gamma ray energy levels. So pretty powerful stuff, but again, it's just a difference in the wavelength between the two. One of the things that we're going to see eventually, when we get to the light dependent reaction, the LDR, is that these photons, the energy within this material from the sun, is going to be what energizes the electrons, okay, to leave their photosystem and begin this process of relocation, which generates energy, which is a major part of photosynthesis. Now, when we're thinking the electromagnetic spectrum, we want to think about, as I mentioned, that spectrum between the radio waves all the way out to the gamma rays. But what we're focused on is the visible light portion. Now, again, we talked about wavelength. For a radio wave, the waves are very far apart. Okay, a much softer level of energy. And for the gamma rays, they are very, very close together. which makes it much more powerful. So looking at this particular spectrum, and you can see spectrums that every one you see is the ends can be flipped. It's just a gradient between the two ends that is the focus. So it doesn't matter if it's left to right or right to left. But what we're thinking about is that visible light portion. So if we're looking at those blues, okay, on the far left, they're much more powerful than the reds on the far right. If we're moving from right to left as far as intensity, then it's the same with the visible light portion, that the blues and the violets have more energy than the reds do. And that'll be showcased when we're looking at the lights, the energy that the chlorophyll and the carotenes absorb. But again, the shorter the wavelength, the more energy it has. And in this particular spectrum, the wavelengths on the far right are softer and gentler, and the wavelengths on the far left are more powerful. Again, same image, but some more things that we want to think about, because we're going to start looking at the chlorophylls and what they absorb, the range, okay, that they do or they can absorb the light energy. It's called the absorption spectrum. Spectrum is always referring to a gradient or a range of numbers. But the idea when a photon, that visible light, strikes a molecule, there's two things that are going to happen. It's either going to be absorbed, or it's going to be reflected or lost as as like heat. And of course, the main function of this is going to be to energize those electrons so they basically leap out of the particular photosystem. But again, that's a topic for a later video. So when we're thinking about that absorption spectrum, we want to think about the reason why like UV or X-ray or gamma rays are not used or not absorbed, because they're just too strong, they're too powerful. Okay, and when they, like a UV that we can kind of absorb, our skin kind of does kind of absorb that. I mean, it does some pretty powerful things to our skin, some very damaging things to our skin. Of course, the whole idea of getting a tan and tanning booths, those are popular notions, and nobody wants to go through the summer, the spring, just completely white, which I can't always avoid. But it does literally just burn our skin to make that brown tone. And of course, X-rays, we know what X-rays can do. I mean, technicians that are in there on a regular basis performing X-rays, either one are completely out of the room, away from it, or lead vest, lead outfit, that kind of stuff. And of course, gamma rays, we understand their potency there. But anything with a wavelength smaller than 400 is just too powerful to use. And if it's over 700, which is the rate of the reds, then there's just not enough energy in them to get the job done, to get those electrons energized enough to leap out of their photosystem. So here's our first look at the absorption spectrums of the various chlorophylls and carotenes. And one thing that will hopefully jump out at you is that you don't really see a lot of these graphs of what they can range in the green section. Okay, and from a logical standpoint, the visual evidence of that is the reason why we see plants as green. It's not that they're actually green, per se, but that's the portion of the light that isn't absorbed. And if it's not absorbed, then as I mentioned earlier, then it's reflected back, and that's the color that we see. So something we're going to talk about in video 2, there are particular carotene. You can see B-carotene listed in there. There are other carotenes, and they are responsible, or not responsible is the right word, because it's an inverse relationship between what we see and what's absorbed. So by them not absorbing a particular color and absorbing everything else, that's the color that we see, like the red of a tomato or the yellow of a banana or the orange of an orange peel. It's the same concept. But looking at chlorophyll A, which is the main chlorophyll, there's about 5 types of chlorophylls, but only A and B are really used in plants. The others have specific functions in specific organisms, like bacteria, the protists that I mentioned earlier. But chlorophyll A, not only is it the main one, but it's the chlorophyll that's around the electron. When we start talking about the reaction center in a later video, a component of the LDR, the light-dependent reaction, the chlorophyll A is the one that's around that, and it absorbs. It's the solid line in the graph, if you're looking at the key. It absorbs in that 400 to 450 range, which, if you remember from the electromagnetic spectrum, that's the blues. That's the blues, the darker blues. And then also in that 650 to 675 range. The chlorophyll B is just kind of inside on each of those numbers, 450 to 476. I didn't really mean to be that accurate. It should have been a 5, just a general number, 475. And in the 625 to 650s. And in the B carotenes, again, these are accessory pigments. Chlorophyll A being the main one, chlorophyll B, B-carotene. They kind of pick up colors and energies that the A's can't, is not within their range. But as I mentioned, greens and yellows are not absorbed; they're reflected. So that's why a lot of plants are green essentially, and if they're not green, it's yellow or some kind of a combination of yellow and green. And that's the reason why, because those colors aren't absorbed and they're reflected back into us. Well, that's our video over pigments. When we come back, we're going to look at part 2 of the pigments. So we'll see you then.